Let's define yet a few more functions on lists to practice even more what we have learned so far. First function I want to define is drop. We have already seen take and drop before. So again, before I actually reload and lose access to my Prelude version, let's briefly recap what take and drop are doing. So take and drop both have the same type signature. They both take an integer and then a list of arbitrary element type, and they produce another list. Take takes the first few elements out of a list. So if I give a list such as the numbers 1 to 10, I get the first 3 numbers out of this list. Drop removes the first, in this case, 3 elements from the list. So we'll keep all the others. So the general idea is that if you take a certain number from a list and you drop a certain number from a list and you put the two things, the two results together, you get the original list back. In fact, there is a function that does both at the same time that is called split at, which we may look at later. So I want to try to define drop here. I mean, although take works according to relatively similar principles. So let's start with the type signature as usual. So we'll write the type signature, and then I'm going to give names to the arguments. Let's call the integer n or perhaps I and the list access. Now, the fact that we have an integer that we operate over is a little bit new. And also one thing that will be interesting here is that the integer actually does matter, right? Because if we have a non-empty list, again, I have not reloaded here, so I can still use the Prelude version to gain experience with what we're actually trying to re-implement. So if we have a non-empty list, right, and we drop no elements from it, 0 elements from it, then we get the entire list back. But if we drop an element from it, like say 1 or more elements, then we do not get the entire list back, right? So whether the first element of a non-empty list ends up in the output does depend on the number, right? So this is going to be a little bit interesting. And indeed, there are different strategies here, what we are doing with the integer and with the list in what order. But because we have experience with lists now, let's try to do a pattern match on the list and see how far we get with that approach. Okay, so let's try to split on the excess and introduce, as we have done many times now, these two cases. And now the first case is actually also interesting in the sense that what do we actually do if we drop, say, 5 elements out of the empty list? And while we are at that, what do we actually do if we drop -5 elements out of anything? So these are questions that we should be answering. And you might think that, well, that is just bad. We shouldn't do that, and we should probably throw an error message. And indeed, you could argue that that should be the case. But one thing to keep in mind is that in Haskell, you should always try to write functions that are total. Total means that for any valid input, like any input that has the right type, we should be aiming to produce a valid output. That means an output that actually has the right type. We should not try to crash. We'll come back to this very soon, to this, like what we could be doing instead of crashing. But crashing is generally discouraged. So in the absence of crashing, what else can we do if we are promising to give back a list? Well, we have to somehow find a plausible result to give in these strange cases anyway. And so what the Prelude version of drop is doing is if we drop more from a list than is there, right, then we simply still drop everything. So this is like try to drop 5 elements from the list, right? But if you if you run out of list elements to drop, then just stop, like just return the empty list anyway. Okay, that that is okay. We can implement this as well. And then with negative elements, that's even stranger. So I mean, that is something that I argue probably should really not be done. But the decision that the Prelude version of drop makes here is to simply treat dropping negative numbers of elements just as dropping 0 elements. So so drop -3 is behaving exactly in the same way as drop 0 would behave. Okay, so let's try if we can reproduce this Prelude behavior. I'll now go to reload here. I'll get the version with the holes. I'm losing access to the Prelude version in my interpreter. We are going to this now. So, but that in particular means that in the empty list case, we can now just return the empty list independently of what I is, because the list drop is only going to make the original list shorter ever, right? And if we start out with an empty list, then we have no other option than to return the empty list. But in the case where we have xcons x's, as I said, now it matters what I is. Okay. And now it matters whether I is 0 or whether I is greater than 0. And look what I just said about negative numbers. Negative numbers are treated as 0. So if we were not interested in negative numbers, right? So if we would completely ignore negative numbers, we could actually use pattern matching even on an integer. We can use pattern matching. That is a little bit of an exceptional thing. We can use an integer literal as a pattern and have a case for 0. Okay, but we cannot have a case for 0 and all negative numbers by means of pattern matching. We need a Boolean condition there, like an if then else or a guard, which we'll get to. But if we only were interested in filtering out the case for 0, we could have a special case for drop 0 xcons xs, and then have another case for the general drop I xcons xs. And here now, these two cases are overlapping, as it's called, because I would also match 0. So here the order of the two cases is really important. Pattern matches are in principle occurring, are matched in order, only that most of the time we try to make them non-overlapping, so then their order does in practice not matter. But here I could match 0, so we have to make sure that the 0 case comes first. And then in the I case, we implicitly know that I is not 0. Okay, so what will we do now? If we drop nothing from a list that is of shape xcons xs, we just return the list as it is, xcons xs. And if we drop something that we know now, because we ignore negative numbers for the time being, to be greater than 0 from xcons xs, then we drop the x. Then we actually discard the x, and then we make a recursive call, but now with a changed I, with I minus 1 to the rest of the list. And in this case, we really discard the x. So we can replace the x here with an underscore, and in this case here we are really not interested in the I, so we can replace this with an underscore as well. So this version of drop loads, and this version of drop actually works fine for all non-negative numbers. It just works strangely for negative numbers in that rather than treating negative numbers as 0, it does treat negative numbers in such a way that apparently it always removes everything from the list and always returns the empty list. Why did I get this extra? Oh, I think I accidentally hit the key. So drop with a negative number always now seems to return the empty list. Why is that? Let's briefly look at this. If we call drop with a negative number and a non-empty list, then the first case does not match, the second case does not match because we have a negative number here. So the third case matches. So we go on and call drop again. We drop the first element, we call drop again with an even lower number, so still a negative number, and a shorter list. So we'll never match this case 22, which is the only of the three cases that actually produces an element in the result list, because we'll never hit 0. So we'll run through the list, always hitting this final case until we hit the empty list. And if we hit the empty list, we just return it. So with this version of drop, we have a different behavior than the prelude version of drop because we treat negative numbers differently. So if we want to be faithful about the re-implementation, then we have to use guards or if then else. And again, I'm going to briefly show both these options. So let's first do if then else. So then we would just have one case like this, and then we would say if I is less than or equal to 0, then we are in the situation where we want to return xcons access. Right. Else, we are in the situation where we want to make the recursive call to drop with I-1. Okay, and now drop still works correctly for normal situations. It also works fine if we call it with a too large number, we just get the empty list. And if we call it with a negative number, we get the same result as with drop 0. Okay. And this can be rewritten to guards very easily, again by just putting the condition in a guard, removing the equals from there. Here we put this case, and then the else case we replace with an otherwise. And then it's probably best to, again, either align all the equals symbols or none of them. So let's do it like this. And this version also works. Right? Okay, that's all I think there is to say about drop. Let's tackle one more function, and that is append. So append is actually available as ++, as an operator called ++. Right, so append appends two lists to each other. So and of course append also works on strings, because strings are lists of characters. So we can do something like this. Right, and it also works on lists of any other element type. So perhaps this is slightly trickier because it's an operator, a symbolic operator, just because that makes the definition look more noisy. So as a first step, let's actually not hide the ++ operator, but let's just define append as a function. That name is free. To do the same thing as the ++ operator. So the ++ operator actually has this type list of A to list of A to list of A, right? It needs to take two lists of the same element type, otherwise you couldn't combine them into a single list. And let's try to complete this. So here we now introduce two names for the argument lists. And now we have a choice, right? Now this is a place where one can easily get into chaos if one has multiple structured inputs, and we could start pattern matching on either of them or both, or right. So it's a little bit important to stay systematic here, right? And we really have a choice. Do we pattern match on the first, or do we pattern match on the second list, or do we try to even pattern match on both? And you, first of all, as a rule of thumb, you should never just start out pattern matching on both or on all arguments. You should try to always be systematic and start splitting across one argument first, and then see whether you actually need to like make further case distinctions in some places, right? But that still leaves the question: if we want to start out with 1, do we start with the first or with the second? And here there is a clear right answer in this case. The first argument is best; it leads to an easy result. The second argument is worse. Intuitively, the reason is that lists are asymmetric as we've defined them, right? We have cons as the major way to build lists, and cons prepend something. So that means that if you look at a list, you have easy access to the beginning. You can immediately identify what the first element of the list is, and you can operate on that in some way and then operate with the rest. Whereas accessing the end is actually tricky. You have to go all the way through the list in order to look at what is actually at the end. And if you try to append 2 lists to each other, then it is easier, again, to operate at the beginning. Well, if we start splitting on the second list is going to be put in the end of the first. So we somehow have to operate then in the middle of the whole structure if we start pattern matching on the second list. And that's what's making it different. So let's try the successful approach first, at least. So let's try doing a pattern match on the first list, and then we get these 2 cases. And let's try to see if we can actually come up with a solution here that works. So in the first case, we are trying to append an empty list to another list. That fortunately has a very simple answer. If we append 2 lists and one of the 2 lists is empty, then we simply have the other list. We keep the other list as the result. So ys here is the result of appending the empty list to it. And if we append x cons access to ys, now the thing that should be in the back of our minds is the recursive call. We probably want to make a recursive call on append xs. And probably, in most cases, the other arguments do not change. Sometimes they do, like in the drop case, we changed the other argument from I to I-1, but often we just, like, the other argument is just staying unchanged. So the first candidate for the recursive call would be append of access to ys. So let's assume, right, we are trying to append 1, 2, 3, and 4, 5, 6, right? And now let's assume further that we have already successfully appended the tail of the first list, which is 2 and 3, to the second list, so that somehow we already have, from the recursive call, append access ys. Let me write that recursive call here. We have already received the right result. Then what do we need to do to this result? Right, what do we need to put here in order to get the correctly appended complete lists 1, 2, 3, 4, 5, 6? We just have to prepend this one element, x, and we can use cons for that. So we can just use, so in this case here we could write 1 cons, right, for this special case. And in this general case that we are programming here, we can just write x cons. Right? And then I don't need the parentheses here because it's a function application versus an infix operator. Again, function application binds more strongly than any infix operator. And this actually works. So now if I try this call, I have to reload. I'll actually get the right result. Okay. And what other examples did I have? This one, if I call this with append now, I get the same result. Or I could use append and infix position as well here by enclosing it in backticks. Okay. So this leaves a few loose ends. One aspect is we could see what happens if we started pattern matching on the second list instead. This is something that you might end up doing if your intuition fails you, that you pattern match on the second argument first, and then you get these two cases. Okay. And again, the first case is simple, because if you append the empty list to the end of access, you still also just get access. Okay. But now the second case is really hard. Okay. Because now you know that the first element of y, of the second list is called y, and that the second element list is not empty. But in order to make a recursive call, well, I mean, what kind of recursive call could we make on the tail now? We could say, like, we would want to make a recursive call with append of ys, but now what we have to put in the first element somehow needs to, like, include the y and the xs. And in fact, we would have to somehow append already the y to the xs, or we need to know more about xs as well in order to do this. I mean, but in any case, we're kind of stuck here. We either need another function that we don't have at the moment that appends a single element into the end of a list, or we need to do further pattern matching on xs. And I guess if you started out with a doubt as to which of the two arguments to pattern match on, and then you get into a tricky situation like that, that should be an indicator that you should try perhaps the other approach, whether that leads to success in a more easy way. So I guess at this point here, you should, given the fact that you had these two choices which to pattern match on, you should recognize that this is going to be tricky. So perhaps the choice you made wasn't right. Okay. So that settles that. The other thing is that, of course, we actually wanted to re-implement the plus operator. So in order to re-implement the plus operator, we have to hide it from the prelude. And now, given that we have defined append, one easy option that we have is to actually just use the function that we've already defined. And we can really do it like that. We can say the function plus is equal to the function append. There's no problem with the definition being like this, where we don't introduce names for the arguments at all. We simply map something of a function to the right type. If you look at the whole here, right, the whole here says we have to provide something of type list of A to list of A to list of A. And the append function does have that type, so we can just write it like this. I could also give names to the arguments and then pass them on. That means the same thing, essentially. And I could also put plus in infix position, which would make this more idiomatic. That would also work. All these versions are essentially the same. Okay. And if I already have append, then obviously defining the operator in this way is a good idea. Okay, but if we had not yet defined this, we could also have defined plus directly via pattern matching, and it wouldn't change very much. The only difference is that rather than defining append here, we define plus here, and we use this symbolic, and in this case infix notation, but we have the same two cases to consider. Then we have the empty list plus ys, which is giving us ys, and we have xcons xs plus ys, which is giving us, right, now we have to be a little bit careful, xcons, and now xs plus ys, right? So this is the recursive call. And note that I'm putting parentheses here, but I'm going to say something about these parentheses in just a moment, right? So this loads, and this is exactly, look, this is exactly the same definition structurally than that one. Only our calls to the prefix append function are all now written using the infix plus operator, and our redefined plus operator works as expected. Okay. It does look a little bit funny though, because if you look at the left-hand side and the right-hand side, really the only difference in line 32 here in the cons case is the placement of the parentheses, right? So we have x cons xs plus ys on the left hand side, and we have x cons xs plus ys on the right hand side. The only difference is that here we are trying to append two lists, the first one of which is a cons, and here we are consing something to a second argument, which is an append, and that is a substantial difference. And I would say that this subtlety alone is enough to say that these should be written with parentheses. But also note that we are just defining plus plus, so its priority is in our hands, right? So if you define an operator, you should give a priority to it. So now if I drop off the parentheses and call this, what's going to happen? Right? Is it still going to do the right thing? Yes, it is. But why? So what is the default priority of plus plus, the one that it gets if we don't put anything, an explicit infix declaration on? This is very, very subtle, and you should not rely on that. Default priority of operators that you're defining is very high, right? So so you should give an explicit priority declaration. And in fact, the one that is used in the prelude is infix R5, which is exactly the same, right associative and priority 5. It's exactly the same as the priority of cons, which means that if both cons and plus plus appear next to each other, they're just bracketed to the right because they're both right associative and of the same priority, which is the right thing to do here. But it is really so subtle that I would put the, like, strictly speaking, redundant pair of parentheses here. Okay. Now, as a final function that I want to discuss in this video, let's look at reverse. So again, this is one that I'm going to hide because we are re-implementing this. And let's have a look at a reverse where I've not reloaded here yet. So reverse is of type list of A to list of A, and it just reverses a list, reads it from right to left. And let's see if we can come up with a definition according to our standard principles here. So I'm introducing a name for the argument, and I'm doing a case split. This should all be second nature by now. And I'm keeping in mind that I want to call reverse XS in the cons case. But let's first focus on the nil case, on the empty list case. If I have nothing to reverse, then I produce the empty list again. And now here, I want to reverse XS. And let's again do some sort of example here. So if I have reverse 1, 2, 3, and I now assume I've already reversed the tail, so the tail is 2 and 3, I already have 3, 2, right? So how do I get 3, 2, 1, which is the reversed full list, from having reversed the tail correctly, if I assume the recursive call is working properly? Well, I have to append the 1 to the end of the list. And I said, while we were defining append, that appending an element to the end of the list is something that we cannot easily do. Like while we were exploring the pattern matching on the second argument of append. But now that we have defined append, we can actually put a single element into the end of a list. By using append, we can put X into a single element list and use the append function or the plus plus operator to put the X in to the very end. Okay, so this type checks, and it seems to work. And if I execute it, it actually seems to be working okay. I will already say, though, that this version of reverse is very, very bad. It performs very badly. It has quadratic performance, where intuitively reversing a list should be linear in the size of the list. Why does it have quadratic performance? We can also already look at that. The point is exactly this call to plus plus here, right? And I said that accessing the beginning of a list is very easy. Accessing the end of the list is very difficult because we have to go through all the list in order to identify the end and then do something there. If you look at what the append function does, it does exactly this. It traverses the entire first list until it hits the end of the first list, and then it kind of replaces the empty list with the second list. But we always perform a traversal of the first list for every call to append, right? And now we're calling append for every recursive step on potentially very long lists, right? So this reverse start is being called on a potentially very long list, and then we call reverse access again on a potentially still very long list, right? If we start out with a list of 100 elements, then this first recursive call here will still be on a list of 99 elements and produce a list of 99 elements. So we'll have to traverse a list of 99 elements in order to append this one element. And then we have to do it again for a list of 98 elements, and for a list of 97 elements, and for a list of 96 elements, and so forth. So all these traversals, they add up to quadratic performance, and that is not good. We'll get back to this point at a later stage in this course. Okay, but for now we have been nevertheless successfully implemented 3 more functions on lists. We have implemented drop, we have implemented append in both the operator form and in the textual alphanumeric form, and we have implemented a slow version of reverse, but that has the advantage of being very simple and straightforward to implement. Okay.